Okay, so let's start. So I'm Maciek Lewenstein. I will be chairman today, and good morning, everybody. We are starting the second day of this beautiful school, and we have a great honor and pleasure of having Roman Krems with us. Roman graduated in Moscow State University. He spent some time in he did PhD actually in Göteborg in Sweden, then spent quite a lot of time in Cambridge, Massachusetts at ITAMP and Harvard MIT, working on cold molecules, and finally got a tenure track position, and then got tenured maybe 12 or 15 years ago at British Columbia. University of British Columbia, where he is a full professor now, and his specialty are cold molecules and their properties, but in particular applications of machine learning to quantum chemistry. Roman, the stage is yours.
Well, thank you, Maciek, for this wonderful introduction, and thank you, Anna, and thank you, Mika, for inviting me to present here today. Can you hear me well and loud?
Yes, it's perfect.
Good. And you can see my slides. Wonderful.
Yes, exactly.
Yeah, so I'm very excited to present, to share with you my enthusiasm about machine learning and applications of machine learning for solving quantum problems. And so here's the outline of what I was planning to discuss. So I'm going to have, I was told that I would be given 3 days of lectures, basically 2 hours over the next 3 days. We're going to start with part 1 today, part 2 tomorrow, and part 3 the day after tomorrow. So what we'll talk about today are some preliminaries, basically some of the basics that will hopefully help us understand what I will try to convey to you in terms of applications of machine learning to solving quantum problems, as well as the discussion of quantum machine learning on day 3. So what we'll do today is start with the discussion of Hilbert spaces and the reproducing kernel Hilbert spaces, the RKHS, and then we'll talk about the standard methods of machine learning, such as kernel SVM, kernel Ridge Regression, and Gaussian process regression that are examples of solving regularization problems with RKHS. So this will probably occupy the entire 2 hours today, and it can be quite mathematical at times. You don't need to understand all of the math, and I'll tell you when you don't have to understand the math that I'll be presenting. But I thought it would be useful to go over it to set the stage for the discussion tomorrow. And the discussion tomorrow is going to be focusing on some of the more applied aspects of what we do, when it comes to machine learning. And so in particular, we'll talk about applications of Bayesian optimization for inverse quantum problems, for solving inverse quantum problems. We'll talk a little more about the basic concept of machine learning. In particular, the focus is going to be on model selection metrics, because it's going to be quite important for our applications in these presentations. One of the key questions that I will address, and raise and address again and again throughout these discussions is how to design the best kernels for the machine learning models that we're going to work with. And for that, we need to understand the model selection metrics. Okay, and then we'll also talk about how to use the kernel selection or kernel improvement algorithms that I will discuss, I guess, tomorrow, how to use this for accelerating Bayesian optimization. And on day 3, we're going to move on to some other applications of the methods that we will be discussing today and tomorrow. So in particular, we'll be talking about applications of Gaussian process regression for building highly accurate potential energy surfaces for very large molecules with something like 50 degrees of freedom. And as well, we're going to talk about using machine learning models, or building machine learning models that are capable of physical extrapolation. And we'll focus on applications for extrapolation in Hamiltonian parameter spaces. And I will conclude my series of lectures by a brief discussion of quantum machine learning. And by that, I mean machine learning that uses quantum computers to build kernels for machine learning models. And one of the central questions there will be how to build the best quantum kernels. So for that, you're going to have to wait, I guess, for tomorrow or the day after tomorrow. So it's midnight in Vancouver, but I'm really happy to be up and talking to you. Right. So you'll probably have questions throughout my presentations. So we were just talking about questions. I mean, first of all, feel free to interrupt me in whatever way you can. I don't know if you can raise your hand or just shout, but feel free to interrupt me. No problems there. Another option could be to submit questions about anything you see today to me by email, or Anna just reminded me that there's also the Discord platform, which I will check tomorrow morning my time. So if you have any questions that you post them there, and I will do my best to address them at the beginning of my presentation tomorrow. Now, how do we structure this in terms of breaks? So we have 2 hours. How many breaks do we need?
It's up to you. I mean, we welcome at least one 15-minute break, but it's up to you how to how to
one 15-minute break.
Yeah, at least, yes.
Okay. So why don't we go for something like 45 minutes, then take a 15-minute break, and then maybe have another shorter break in the middle of the second part. So let's see if we can do that. We'll probably not go through everything I've prepared for today, but we'll see. All right, so let's start with preliminaries. So what we're going to be talking about today is primarily regression and classification models, with a focus on interpolation in the regression case. And classification, is going to refer to problems where you have basically clusters of data representing different classes, and you want to build a model that will classify the data. Okay, so machine learning, if you think about it, at its core, it really boils down to something like linear regression, which is basically putting a line through data that looks like this. Okay, of course, not the reality is most often not linear, but it can be made linear by some sort of a transformation. For example, in this particular case, the change from x to phi of x, with phi of x being x times sine of x, transforms this graph here, or this set of data points, into the green set of data points, to which we can then apply linear regression. So we can perform linear regression on this data set and then transform back, and then this will give us this blue curve that represents nicely the green data. So can you see my mouse when I move it around?
Yes.
Good. All right. So the problem, of course, is that we don't always know this transformation phi of x. In this particular example, I knew this transformation because this is how I designed these data points. But in general, when you're dealing with a general data set, you don't know this transformation. So some machine learning methods, like, for example, those based on neural networks, they aim to determine these nonlinear transformation explicitly. But then there's other methods of machine learning, like kernel methods in particular, that bypass this problem. And they do that by using what people call the kernel trick, which we should thank Hilbert for, and we're going to see why in a moment. But what the kernel trick is, it really boils down to, well, it avoids the need to determine this phi of x explicitly, and it basically writes all models that machine learning models in terms of inner products of this kind. So where these inner products are in some Hilbert space that we're going to talk about. Okay. So we're going to be using the word kernel, I guess, throughout my presentations very often. So let's maybe begin by defining what we call a kernel, or what do we call a kernel actually. So in general, you can think of kernels as weights, whether in a sum or an integral. For example, if you have a sum over some values of some function at x sub I, it can, the values of this function can come with weights of this sort. So this is what we would call kernels. And in an integral, this part here, it's sometimes called the nucleus of the integral transform, or the kernel. Okay. Now pay attention to these examples; they will be useful for us today. So let's talk about the first one of these examples here in a little more detail. Okay. So if we take if y of x sub I is an observation at x sub I, let's say you have some variable x which represents your input space, whatever that is, and at certain discrete values of x sub I, you have some observations. So if y of x sub I is an observation at x sub I, then you can build a model. So when I put a hat over the symbol, this basically means a model. So it's an estimator. So it's a machine learning model. So we can build a model by simply summing these observations at different points x sub I with some weights, and these weights are gonna we're gonna call them kernels, and this is an example of a kernel smoother. Okay. So it's a very simple machine learning model that actually is surprisingly good. So let's take a look at it in a little more detail. So what I have on the slide, up on the slide here, is the simplest imaginable machine learning model. So you have a set of data points represented by those red dots here. And if you want to make a prediction, you want to build a regression model, for example, you want to make a prediction at any arbitrary value of x. I mean, the easiest way to make this prediction is simply by taking the average of all these points. Of course, this is not going to be a very good model, right? But that is a place to start. We can make it better. We can make it better by averaging the data points locally. So if we, for example, average only 10 points at a time, that would give us something like the blue line shown in the lower right graph here, and that's what we call a moving average. Okay. Now this is a much better model of our data, but of course, it's still not something that we would like, because it's very not smooth, and for obvious reasons, it's not perfect, right? So we can perform such averaging for every point in x. Okay, for example, we could center this averaging in every point of x, and then take 10 points around x, each with the weight of 1/10. Okay, and then build a model like this. So this will give us the blue line shown in this plot here. Okay, so something that represents the data now fairly accurately, except that as we can see, it's very non-smooth, and the data here, they come with noise. So basically, what we're doing here, we're fitting every data point here, and we're basically fitting noise. Okay, so what we're going to do to avoid this, we're going to now replace these weights here, in this particular case, they're just 1/10. We're going to replace them with some smooth functions of x. Okay, and in particular, we're going to be using functions that depend only on the distance from the point xi, the point xi, so it should be xi here. So such functions are called radial basis functions. Okay, and the particular kind of radial basis functions that we'll use in this example, they're called Gaussian, renormalized Gaussian functions. So basically, we're going to use these sort of functions that are normalized by the sum over all of this. Okay, so and then if we do that, if we use these functions as weights in for our observations, again we're summing over all our observations and we're using this sort of renormalized Gaussian functions as weights, then we get this blue curve that we think represents the data nicely. Okay, so what we are doing here is simply again summing over observations with weights that are given by the corresponding radial basis functions, and these radial basis functions, they're shown, they're centered on each data point, and they're shown by these curves here. Each curve of a different color corresponds to each different data point here. And so if you want to evaluate your model at a particular point of x, which is x star here, you're just taking all of these red dots and you're taking them with weights given by the value of the corresponding function right at this point. Okay, so basically we have this equation here, and where these weights again are kernels. Now, the reason I'm going through this in such length is because we're going to be talking about more complex machine learning models later on, but I think this serves as a very good reference point for the more complex models, and we're going to come back to this simple equation. We're going to compare those more complex equations with this kernel smoother later on. Any questions so far? Nothing? So I'll just,
I don't see anything. Yeah,
I'll just keep going. Okay, let's go back to our integral transform, the second example. Okay, again, we I guess encountered this sort of transforms in our math courses. So this part here is the nucleus or the kernel of the integral transform. In path integral formulation of quantum mechanics, for example, you're also working with kernels that are given by the Green's function of the Schrödinger equation, just to give you another example of kernels. But in any case, so we're going to be using, we're going to be looking at these sort of integrals now. So back to Hilbert. So what Hilbert showed is that the integral, over two real valued square integrable functions, f and g. So the integrals of this kind, they have the same properties as a scalar product of two vectors in a Euclidean space. So for orthogonal functions, this means that we have this equal to 0. Now, why is this important? Why is this important? Well, the scalar product in the Euclidean space can be used to define the angle between two vectors, right? So, so the scalar product determines the relationship between vectors A and B. Okay, so Hilbert's inner products, they can be used to define the relationship between functions f of x and g of x. And so this can be used to define a Hilbert space. So we're going to be talking about spaces. So if you think about it, what is a space? Okay, what is a mathematical definition of space? If you go to search for that on Wikipedia, you'll find actually that there's no rigorous definition of space in mathematics. I guess more or less a space is a set of elements with some rule that provides the relationship between the elements. Okay, so Hilbert's inner products, they provide the rule for a set of functions. Basically, they provide the relationship between functions which form a Hilbert space. So you have the set of functions, and you have a rule or the inner product that provides the relationship between these functions, and that gives you a space which we call a Hilbert space. Okay. Okay, let's go back to our integral transform. Let's consider a specific kind of the transform with the kernel here, k of x and y, that is symmetric in x and y. Okay, so we have f of x that's given by this integral here. So Hilbert's discovery of the inner product properties of those integrals implies that the kernel, this quantity here, can be written actually as a sum over some products of orthogonal functions phi sub n and phi sub n of x and phi sub n of y. So where phi sub n with different n are orthogonal. Okay, so if these functions are orthonormal, all of these lambda sub n coefficients are equal to 1. So it's actually very easy to see that the kernel function can be written in this form. So what you need to do for that is take this form and plug it into this integral here. Let's do that. Let's do this for 2 examples. Let's first consider a specific case of f of y being one of those functions from the set of orthogonal functions. Okay, and then we're gonna replace this in here, and k of x and y is going to be we're going to take that green equation from the previous slide. So this green equation and put it into that integral. And then what we have on the right-hand side is this. Now, Hilbert has told us that this is going to be basically 0 when n is different from k and 1 otherwise. Okay, and if that is the case, then this sum collapses to this. And of course, which shows that lambda sub k must be equal to 1 if the functions are all normalized. Okay, now for an arbitrary f of y, again, if we replace k of x and y with the green equation from the previous slide, we have this. And again, we recognize, if we believe Hilbert, we recognize that this is just a projection of f, our function f, onto one of the those functions in the orthogonal set of functions. Okay, so this is like the a sub n, right. So and if we set lambda sub n to 1, then of course we have the basis set expansion of f of x. So the final equality, so this equality here is going to hold provided lambda sub n is equal to 1 for all values of n. So this symbol in mathematics means for all. Okay. So what we have, basically we have like if phi sub n is a set of orthonormal functions. So we can write k of x and y in this form, and this is a very special function. Okay. So now why is this function so special? Well, one way to look at it is this. So let's index it by x and view it as a function of y. So it's going to be k sub x of y. And then we can write it in this form, okay? And if you look at it, so k sub x is going to be a vector in the Hilbert space with those functions as axes, okay? So at the same time, we began with these sort of integrals, right? So and you can recognize then that this integral here is an inner product of basically f and k sub x. So we see that the function f of x is given by an inner product of f and k sub x. So any function in this space can be written as f as the inner product of f and k sub x. And therefore, k sub x, it's a special kind of vector. It's called the reproducing kernel of this Hilbert space because it reproduces any function in this space by the inner product of this kind. Okay. So k of x and y is the kernel function that basically defines a reproducing kernel Hilbert space. Okay, and we're going to abbreviate it as RKHS. Okay. So what we said is that, was there a question? Yeah. So what we said is that any function can be in this space can be written as an inner product of this kind. But what if f of x is is also a reproducing kernel, like k sub y of x? Okay. So then we have k sub y of x equals k sub y, or the inner product equals the inner product of k sub y and k sub x. Or so this is of course the kernel function. So we see that the kernel function is the inner product of these two vectors here. Okay. So because it's an inner product, it's going to have special properties. Okay. In particular, it's going to be positive definite. for example. So let me briefly summarize what we have done so far. So what we have said so far. So we said that a Hilbert space is going to be defined by its elements and an inner product. Is a Hilbert space is an inner product space. And if they define the inner product like this, it's the so-called L2 Hilbert space that we're dealing with. Okay. Now the inner product doesn't have to be defined like that, as we will see that for RKHS the inner product is going to be somewhat different. But you need to define it in a particular way, and once you have it defined, it's going to define your space. Now the kernel function k of x and y defines a unique RKHS and vice versa. So if you have k of x and y, you have a unique RKHS, and every RKHS has a unique kernel function. Okay, and this is known as the Moore-Aronszajn theorem. Now, because k of x and y is an inner product, it must be a positive definite function. And this raises the question, can any positive definite function that takes two basically real variables on input and produces a real number on output be a kernel function? Okay, and the answer is yes, if the inner product is appropriately redefined. Okay, so this, let's go back to this inner product that we started with. So this inner product can be written in this form, obviously. So where these are the inner products of f with one of the ng with one of the basis functions. Okay, now consider an arbitrary positive definite function k of x and y, that corresponds to this eigenvalue with this eigenvalue equation. Okay, so now because k of x and y is positive definite, all of these lambda sub n are going to be greater than or equal to 0. Okay, so we're now dealing with a function. Well, we're not arbitrary function. We're not saying, basically, before we started with saying that we started by defining k of x and y as one that satisfies this integral. So we're now saying that this is no longer the case. So we're dealing with an arbitrary positive definite function. Now in this case, you can still write k of x and y as this sort of an expansion, but lambda sub n are no longer going to be equal to 1. Okay, they're going to be all greater than or equal to 0, but they don't have to be equal to 1. Okay, now the question, of course, that we raised on the previous slide is whether this function here, or this element here, is still a reproducing kernel. Okay, so the answer is yes, if we redefine the inner product of the Hilbert space to be this. Okay, why do we want to define it in this particular way? And you see now I'm going to be putting the subscript h here to say that this inner product is going to correspond to that particular Hilbert space that we're talking about, the RKHS. Okay, you see, like if we define the inner product like this, and then look at the inner product of f and k sub x in that RKHS, then we have then we have this, right? If I were so we have, using this equation, we have this. Okay, but now what do we have? So now this thing here, if we go back to so this thing here is just going to be phi sub n times lambda. If you go back to this equation here, okay, from this equation we just get lambda sub n phi sub n, and that lambda sub n is going to cancel the one in the denominator, and we have just that. Now this inner product is defined on the this is the inner product of the L2 space, not the RKHS, and of course this is again the familiar basis set expansion of f of x. Okay, so basically what we see here is that a choice of a real positive definite function k of x and y defines the RKHS by defining the basis, so this function is phi sub n, and the inner product of the Hilbert space, this inner product here, through the eigenvalue equation, through this equation here, because we need to know these lambda values that enter this inner product equation. Okay, now this is actually going to be quite important in general for machine learning, but also particularly going to be important for quantum machine learning, as we will see maybe on day 3 of our discussions. Okay, so now this is all mathematics. How is this all related to machine learning? Well, remember a feature map that we started by discussing. So we have basically we're mapping x onto some high dimensional vector 5x by this feature map. So we will define this feature map so that the inner product of 5x and 5x prime is a kernel function for a Hilbert space in which our data are linear or linearly separable. Okay, now what does this give us? Okay, so this is where we need to talk about regularization problems. Okay, so what is regularization? Okay, so what time is it? Okay.
35 minutes.
Yeah, so we still have some time. Yeah, let's talk about this slow. So what is regularization? Okay, so let's say you have there's this nice image from Wikipedia that I took from Wikipedia. So let's say you have a bunch of points represented by the red dots here, and you're building a model of those points. Obviously, there's an infinite number of models that you can build, and you can build a green one that we intuitively believe is a good representation of the data, or you can build a blue one that goes through the data points, but of course it looks like it's not a very good model. To us, to a human eye, it doesn't look like a good model. So how do we choose a better model in this case? Okay, so how do we train a machine learning anyway? So in general, we want to minimize the distance between the data and the field. Okay, so an obvious choice is to minimize a function that looks like this, where y sub I are your observations, and f of xi is the equation that models the observations. Is the function that models the observations. Okay, so yeah, you want to minimize the distance between them. So you could maybe just take the square of this and sum over all of the observations, and so that's going to give you a functional that we call the loss function. And yeah, so an obvious choice would be to minimize this, but is this a good choice? Okay, so now imagine replacing linear functions in the linear model, so of this kind, where x is just a vector of of x corresponding to different dimensions, whatever your input space is. So just a linear model written in this way. So imagine replacing those linear functions in this model with some other functions of arbitrary complexity. So you're doing this sort of mapping. So if no bounds are placed on the complexity of those functions, so obviously, I don't know if it's obvious, but one can show that the minimization of this sort of a function is going to lead to zero loss function. So you're going to basically generate a complex function that goes right through all of the data points. And if you have data that come with noise, basically you're going to be fitting the noise. So this is what we call overfitting. So regularization aims to prevent this. Okay, again, so if you have a bunch of data points with noise, and you try to fit it by minimizing the function that I just showed you on the previous slide, without regularization, you're just going to be producing something like this that fits the noise. And with the regularization, you're going to be producing a function that looks more like this. So how to regularize machine learning models? Well, to regularize the solutions, you add something to the loss function to restrict the complexity of the model. And one type of regularization that is often used is the so-called Tikhonov regularization. This is actually a special case of Tikhonov regularization. So basically, if you add this term to the loss function and then you minimize this function by varying the parameters of f, what you're doing here, you're restricting the magnitude of f. Okay, and this particular regularization is used in Ridge regression. So if you are building a regression model by minimizing this sort of a function, you're building a Ridge regression model. Okay, now how do we find the function f of x that minimizes this loss function? Again, so our goal now is to find f of x that minimizes this particular loss, with including regularization. Okay, so well, we know that because this function lives in that high-dimensional Hilbert space, we know that we can write this function as any function in the Hilbert space as a basis set expansion of this sort. Okay, but in general, the RKHS is a very high-dimensional space. In general, it's an infinite dimensional space. So if you just want to do a basis set expansion of this, so this sum is going to extend to infinity. So this expansion is actually not very useful. Okay. So, however, if we are interested in a specific function, f of x, that minimizes the loss function on the previous page. Okay. So there's a set of theorems known as the representer theorems. So one of their results shows that the specific function that minimizes the loss function on the previous page can be written in this form, where the sum extends to over a finite number of training points. So the little n here is the number of dots, is the number of these red dots, which is always finite. So we're basically replacing an infinite sum with a finite sum. Okay, and that's the power of this formalism. Okay, all right. So again, so what we're doing again, so let's actually look at the implications of that, because let me remind you that what we're doing here, we're trying to minimize this function here with this inner product as the regularization term. Okay. And remember that the inner product in the RKHS. Yeah.
Can I interrupt you with a question?
Yes.
So maybe I'm misunderstanding, but if you can go back to the previous slide. So because when we think of like minimization of the loss function, right, we also have this non-convex landscape in mind. But here you propose to like change minimization to, is it like exact solution with this? If you solve this sum, this finite sum, is it exact minimum where we land, and it's a convex problem, or what?
Well, I don't know about the convexity. It may still be, so getting there, I mean, like, you're going to have to find this lambda m coefficient. You're going to have to find the parameters of the kernel functions. We're going to talk about that in just a minute. So the convexity question, I think we should leave for later. But it is an exact solution. So you can write a function f of x that minimizes exactly that corresponds to the global minimum of that loss function here in this form. How to get there is a separate question, which we will discuss to some extent.
Okay, thanks a lot.
Yeah. Okay, good. All right. So, but you see already here, you see that so what I'm leading to is that the form of the kernel functions, because the kernel functions define the RKHS, the form of this kernel functions is actually going to be critically important, especially for the kind of problems that we're going to be discussing, the physics problems. And so already here you can see that the actual mathematical form of this function is going to be quite important, but it's going to be even clearer later. Okay, so for now, I just wanted to address a slightly different question that will be important for our discussion of quantum machine learning in particular. Okay, so remember we said that the inner products in the RKHS, they have to be defined in this particular way, where lambda I, the eigenvalues of the kernel. But what if some of the eigenvalues of the kernel are 0? Okay, so this may happen if the dimensionality of the RKHS is finite. And like I said, this will be important for quantum machine learning in particular, because what you're doing when you're building kernels on a quantum computer. So quantum computers, are represented by a bunch of qubits that define basically a Hilbert space that is necessarily finite dimensional. Okay, and so if you build a kernel on a quantum computer, that kernel is going to correspond to an RKHS is going to define an RKHS that is finite dimensional. And therefore, some of the eigenvalues of the such kernels will be 0. So what implications does this have for the regularization problems that we're trying to solve? Okay, let's see. Not that we now have two Hilbert spaces. The L2 space, the original L2 space, square integrable functions, and the RKHS. This one is the one that Hilbert considered in the RKHS, right? That we introduced today. So now the basis functions, the basis states, phi sub n, we call them. They call for some reason phi sub I now. They're orthonormal in L2. Okay. Now the ones of them that correspond to non-zero values of lambda I, they're going to span the RKHS. Okay. So consider a function f of x. So you can expand it in terms of these functions. Phi sub I, like so. So, and if you now look at the norm of this function in L2, it's going to have, of course, obviously it's going to be this, right? And that's because of the way the inner product is defined in L2. We know that in the RKHS, the inner product is defined in a different way. So it's going to have this particular form. Okay, so you can see immediately that, if some of the eigenvalues of the kernel function are 0, okay, so that this is going to, is going to diverge, okay, and this you can see immediately has implications for the regularization problem, because the norm, well, we have the norm of f right here, right? Okay, so basically what we have is that if the function f of x is entirely in the RKHS, then this decomposition will only have non-zero coefficients a sub I that correspond to non-zero lambda sub I. Now, if a part of this function is not in RKHS, that part of this function cannot be learned using kernel regression. So that's one of the main implications of this. There's another way to look at it, and that is this, right? So machine learning problems, like I said, we solve in machine learning, we solve regularization problems. So what we're doing in kernel ridge regression, for example, is we're regularizing the norm of this function in RKHS. So this is our loss or cost function. So again, if some of the lambda I are 0, the corresponding term in the norm is going to be infinitely large. So when you minimize this functional, the a sub I basically, so I mean, like this function is not going to be sensitive to the a sub I, the corresponding a sub I, the one that corresponds to lambda I equal to 0. So I guess of course lambda I equals 0 is an extreme case, but you can have eigenvalues of the kernel function. Some of them are small, and some of them could be large. And the implications of this is that the larger the eigenvalues of lambda I, the easier it is to learn the corresponding a sub I. And I guess the converse implication of that is that if you have a kernel function who's with all of the eigenvalues that are small, you basically are not going to be able to learn your function by kernel regression.
Sorry, so we have a question here.
Yeah.
Hey, I was just thinking if this has anything to do with a PCA. Like it sounds like a little bit like a PCA here, that you have like basically an eigen decomposition, and then you have like some that are basically like in the data set you have some vectors that are more important and some that are less important. Does this have like anything to do with it?
Yeah, I'm trying to make a connection with PCA. So it's more to do with with the fact that like imagine spaces and imagine a part of your function that you're trying to learn one of the so part of your function is linear in one of the spaces, but it also has a part that lives in the other space, and that part that lives in the other space you cannot learn with kernel regression with this methodology. This is what I'm trying to say here. How to relate this to PCA? Immediately, I don't see the connection. Yeah, it's these are different spaces that we're talking about, the L2 and the RKHS.
Okay,
So
thank you.
I don't know. I'll see if I can make this connection, but I don't see an immediate connection.
We have one more question.
Yeah, please.
Are most overfitting problems solved by regularizing in this way with the norm?
Well, no, actually. So there's different ways to regularize the loss. The solutions. So this, yeah. So if you take the square of the norm and add it to the loss function, that's Ridge regression. It will also be the case for SVM, as we will see today. But sometimes people would regularize the loss function just by not by the square of the norm, but by the norm itself. And then it will lead to what people call lasso regression, for example. That's another example. So yeah, there's actually the freedom in how you do regularization, and there is reasons to do one or another. That it would take me maybe an hour to discuss those reasons. And there's interesting applications to lasso regression that cannot be not as easy to achieve with Ridge regression. So there are advantages and disadvantages to different kinds of regularization. But this is one of the most common ones. And kernel Ridge regression is very powerful. And it's also, I guess, this sort of kernel Ridge regression or regularization in kernel Ridge regression is going to be equivalent to the description of noise in Gaussian process regression, as we will see. So that's why I think, this one is particularly important. I guess another reason why this one is important is because, like I said, I called it Tikhonov regularization, and why it has a name attached to it is because if you have a loss function like this with this particular regularization, you can solve. Like in the case of linear models, you can actually write. You can solve. You can write an equation for the coefficients of the linear model exactly, right? So you don't actually have to minimize this loss function. You can write so there's an expression for the coefficients that is simply written in terms of the covariance metrics. So I guess that's my lengthy answer to your simple question.
Thanks, Todd. We have another question.
Yeah.
Maybe you'll get to that still, but you mentioned radial basis functions as a possible kernel, and it seems like since it seems like the point really is just to smooth, and radial basis functions of course make sense because the closer you are, the more of an impact it has, and it flattens out as you get further away. So is that then the universal solution to every problem to use radial basis functions, or is there any way to adapt the choice of kernel to your problem?
Yeah, so that's you're asking about the crux of my 3-day presentation. So one of the points I'm going to try to make is that the choice of the kernel functions is extremely important, and you have to design strategies to choose to build kernel functions properly. The RBF, the radial basis functions, is not going to be an answer to any problem, and in many cases they don't actually work as well as other types of kernels. So the big question is going to be how to build good kernels for particular problems, and that's what we're going to talk about tomorrow. So that's going to be the crux of the main part of my presentations.
Okay, thank you.
Yeah. Okay. Right. So so what we're saying here is that the essential part of let me just conclude with a couple more slides and then we'll take a break. So what we're saying is that the essential part of building a machine learning model is to find the right kernel function. So how is this typically done? Well, in typical applications of classical machine learning is one starts by assuming some functional form for the kernel function, and here's a list of some popular choices to the kernel function. And then these functions are, as you can see, they're parameterized by a few parameters. Like there's not a lot of parameters, but a few, like D or A1 or A2 or gamma. Okay, so having chosen a particular functional form of the kernel function, one typically varies these parameters to find the best model. and we're going to talk a little bit about how to do that. Yeah, so this is what people normally do. This is not what we are going to do. Like I said, this is not going to work for our purposes. I mean, like it works for many purposes, but like if you want, for example, to build models that can extrapolate physically, that's not going to work. And yeah, so I'm going to hopefully explain how to build extrapolation models to you tomorrow. Okay, so we're going to, I guess, next talk about the more details of how kernel ridge regression and SVM support vector machines and Gaussian process regression work. So I think what we should do now is take a break and yeah, and then so did you say on 15 minutes?
Yes, it would be great.
Okay, then we'll come back at 5 after the hour.
Great. So maybe there are some questions, like, or we can also go after. Yes. Okay. So no questions. Let's go for the break. Thanks a lot.
Yeah, no problem. So
Thank you very much.
Yeah.
So we meet 10:05.
So I'll just stay here and yeah.
Okay,
Maybe.
so Ron, actually, can I have one request? So I think it would be super useful for questions today if you could send the slides, if it's possible, like PDF to the email or to my email or anything. So I will share it with because I think it would be very, very useful. Thanks.
I will do that. Yeah.
Thank you.
I'll email it to you, right?
Yep, sure.
Shall I go ahead?
Yes, please.
All right. So yeah. So let's now take a look at exactly how kernel ridge regression, as well as SVM and Gaussian process regression work. And again, there's going to be a little bit of mathematics in this, and you don't need to understand the details. I'm going to try and emphasize some of the key points that I'm trying to make here. Okay, so kernel ridge regression is a regression model that basically is built by minimizing this sort of a loss function, as we said, with the this particular kind of regularization. It's equivalent to that in ridge regression. Ridge regression is linear regression. So kernel ridge regression is equivalent to ridge regression, except that the model is now it's now in a high or n-dimensional Hilbert space, where n can in principle be infinity. Okay, so yeah, so we're dealing with kernel ridge regression, and because the shapes of the functions f of x can in principle be arbitrary, they're linear in that RKHS, but in the input, the original input space, they're arbitrary. Kernel ridge regression is capable of building arbitrary models, not just linear models. Okay, so how does it work? So to build the model, we're going to start by defining the kernel function, k of x and x prime. And next, we're going to need to find the equations for the coefficients alpha j in this equation that we saw earlier. Okay, so we can write this term in a matrix form like this, and the regularization term can be written in matrix form like so. And then, it can be shown that the solutions for alpha, these coefficients alpha, I'm writing this all in vector and matrix form. So these solutions can actually be obtained like so. So these coefficients alpha, they can be written in terms of the matrix K, which is what we call the kernel matrix. So the Y here is the vector of the original observations. So this is this size of this vector is the number of training points, and the size of the matrix K it's an n times n square matrix, where n is the number of training points, and that's what it says here. The matrix K is a square n times n matrix with elements given by the kernel function values, where xi and xj are just pairs of training points, okay? Pairs of those red dots in my plots. Now, given alpha, given the models of alpha, the estimates of alpha, we can write the estimator of the model at point x star. So at any point x star, we can write the model in this form. Where this vector k of x star is just basically a vector of kernel function values with, kernel functions connecting each one of the training points with a point of interest. Okay, now we should compare this with the kernel smoother that we mentioned earlier in the discussion. So as you can see, the only difference between this and the kernel smoother, well, the only difference, but it's an essential difference. So it's this part here. So if you omit the term in the square brackets, then you'll get the equation that we saw before in the kernel smoother discussion. And you see what the regularization does? So lambda here is what brings in the regularization. It basically modulates the diagonal elements of the kernel matrix. Okay, and that's what prevents the regression from fitting the noise. Okay, so again, what we can see is that the model is written in terms of the vector of observations, the square matrix K, whose elements are the kernel function values, and the column vector K of X star, whose elements are the kernel functions K, X star, Xj. So again, we see that the problem really boils down to finding the proper kernel functions, K of X and X prime. And how is this done? Well, again, you would start with one of these choices. Typically, you would start with one of these choices, and then you would vary the coefficients in these functions by minimizing the validation error. So you're going to have a validation set in your data, which is a part of your data set, and you're going to minimize the error on that validation set. And you could do this, for kernel ridge regression, you could do this either by cross validation or, by grid search. So you would typically vary those parameters actually by grid search. Okay, but that's a minor detail. Okay, now let's talk about the SVM. So for classification problems. So how do we solve classification problems with kernels? So in general, if you have data representing multiple classes, to build a model that classifies the data, we basically build a model of the plane that separates the two types of data points. Okay, except that, of course, as you can see from this diagram here, one can draw many planes that separate these two sets of points, and then the question is which one is the best separating plane or hyperplane if it's in a high dimensional. Okay, so again, and of course the question is, what if the data are not linearly separable? In this case, the way I show the data points, they are linearly separable, which means that I can draw a line in this graph or a plane, in a high dimensional space that separates the data points. But that's of course not always going to be the case. And if the data, like for example, this is an example of a case, where the data are not linearly separable. Okay. Now, again, what these kind of cases can be handled with feature mapping. For example, if you introduce another feature such as like one that is related to the original feature, this x variable, by the sign of x1, then you can place your data in a two-dimensional space with x1 and x2 on the axis, and the data is going to look like this, and you can see that it becomes linearly separable by the x equals 0 line. So this is an example of lifting data to a high dimensional space to make it separable. Okay, we can see that in 1D the classes are not linearly separable, in 2D the classes are separable by the x2 equals 0 line. Okay, so the idea behind using kernels for classification is really basically relies on the fact that there's an RKHS where the data are going to be linearly separable. Okay, and that RKHS is going to be defined by the kernel function that we're going to be using. Okay, so the support vector machine is a method that is often used for classifying data. and including data that are not linearly separable. And so we're going to see a few details about how it works. And the reason I wanted to go through this in detail is because there's a lot of focus on classifying data with quantum kernels these days. Kernels built on quantum computers, and there's like IBM in particular has released a set of Python libraries that allows you to allows us to build quantum analogs of the SVM, and so it helps to understand the classical SVM to understand how quantum SVM works. And we'll talk a little bit about quantum SVM on day 3. Okay, so in the examples that I'm going to show today, we're going to look at this sort of data set where you have two classes arranged like so in the two-dimensional space. So this is clearly a non-linearly separable problem. Okay, now to understand how where kernels enter, let's first consider again the linearly separable problem. And there's this drawing here that does some simple geometry manipulations, but maybe we shouldn't waste time looking at the drawing here. So the only thing that suffices to say here is that this plane here that separates the data points, it is given by this equation here, okay? And the unit vector in the direction perpendicular to the plane is basically beta divided by the magnitude of beta. So where beta is the vector of those coefficients here. So x can be multidimensional, and so the beta is basically is a multidimensional is a vector of coefficients beta. Okay, so again, what this drawing shows is that two things, right? So the equation for the hyperplane is this, and I guess another thing, and I will send you those slides, and so you can convince yourself by looking at this drawing and simple geometry calculations that the shortest distance between any point x and the hyperplane. So like if you take any point here and look at the shortest distance, like between this point and the hyperplane here, the shortest distance is going to be this. In terms of the coefficients beta, is going to be this. So how does one find the coefficients beta and beta naught of the hyperplane? Okay, so one way to determine the optimal hyperplane of the many hyperplanes that can separate the data is by maximizing the distance m from the data points. You see, I can draw a plane here, and now I can denote this introduce m, which is the distance from the data points to the plane. Okay, and so what we want is to maximize the distance from the data points. So the data points, and so I'm going to have a hyperplane. I'm going to have a slab. Okay, like I'm going to have this margin here as a result of this exercise, and the data points that lie right on the edge here of that slab, they're going to be called the support points. Okay, and that's why it's called the support vector machine. Okay, so we want every point to be at least this distance m away from the hyperplane. Okay, so like I told you just a couple minutes ago, the distance of point x from any point xi from the hyperplane is just going to be given by this equation. So we want for each point in the data set, and this, by the way, can be positive or negative depending on which side of the hyperplane you are in, and that's why you're going to be correcting that to make this whole thing positive by multiplying it by yi, which is your observation, and your yi is going to encode the green and the red data points by plus or minus 1, so that this term is always positive. And you want this this term to be greater than or equal to m. Okay, and then you do some simple rearrangement of terms, and yeah, so if you note that if we scale each of the beta coefficients by the same factor, then this inequality is going to be preserved. Therefore, we can arbitrarily rescale beta and beta naught by 1 over m, and then we have this. So this is the condition that we want for every point in our data set. So to find the optimal hyperplane, we want to minimize beta while ensuring, this condition, basically. That's what we want to do, okay? So, we're going to use Lagrange multipliers for that, of course. So we can basically do that by, because basically now we have a minimization problem with conditions, right? So we want to minimize this, with this term here. We want to minimize this whole Lagrange function with those coefficients alpha I chosen such that this whole thing is 0 for each I, which basically means that it's either alpha I that's 0 or this term in square brackets that's 0. So if we take the derivative of that with respect to beta, and then then you've got these equations here, and after setting it to 0, and then so then you can actually take those terms, the beta term, and put it back into this Lagrange function. Okay, and I guess the point of all this is to say that then this will then reduce to this equation, which is called the Lagrange dual, the Wolf dual, and basically this equation here is the lower bound for the actual for the Lagrange function that we saw on the previous slide, and therefore the minimum of L corresponds to the maximum of this, and this is what you actually maximize when you maximize this by varying alpha subject to alpha being positive. And so, and this is what you maximize to when you train your SVM, okay? And once you have the alpha, you basically have the betas, okay? You have the betas through this equation here, okay? There's not much more to say about that, except that, so now, of course, we want to extend this to a non-linearly separable case. Okay, so well, to do that, the first thing you want to do is allow for some misclassification. So we want to allow for some of the points to be on the wrong side of the margin, and those kind of like in the drawing here. And so previously our condition was this, and now if we allow some of the points to be on the wrong side of the margin, this condition is going to be somewhat, modified. It's going to be basically a little softer. So it's going to be this, right? So where this term here is 0, if the point is on the right side of the margin and it's not 0, it's as shown by this these vectors here. If it's on the wrong side of the margin, okay. So yeah, again, this is going to be our constraint for the minimization problem. And as before, we want to maximize the margin or minimize. So maximizing the margin, because the margin is as we said, M is 1 over beta, right? So we want to minimize beta in order to maximize the margin. But we now have another constraint here, so which we will add a cost term to the L function. So the Lagrange function will now be this, and with these sort of conditions. So again, this is not really important. What I'm trying to get us to is the final equation. So the goal is really to find the minimum of that Lagrange function by varying beta, beta naught, and those guys. Okay. So again, we're gonna set the corresponding derivatives of L to 0. And then we get this, and then we take those guys, and replace them into the original Lagrange function. We get this equation here, which again we maximize by varying the alpha coefficients. And incidentally, this is a convex problem, and that's what makes training SVM fairly straightforward. So it's fairly easy to find the alpha I and alpha j. Okay, now. So this is this equation again, and I'm going to write this term in this, as the inner product of xi and xj, which is what this is. Okay. Now we want to deal with non-linearly separable sets, We're going to introduce the feature map as before. We're going to be mapping xi to some high-dimensional vector here. And so just using the previous equation as a starting point, we're going to replace those terms in the inner product by this. But this we've already seen is a kernel function. It's a kernel function, k of xi and xj. So we can write the Lagrange dual function as in terms of the kernel function. Okay. So and this function again can be maximized numerically to find the coefficients alpha I. And I guess the parameters of the kernel function can be found by reducing, by minimizing the validation error. Okay, so if we go back and look at the equation for the hyperplane that separates the classes in this high-dimensional space, it's going to be given by this sum here. Okay, and but the equation for the f of x, again, in the high-dimensional space, we have a linear function of those phi's, right? So we're going to take this and we're going to multiply it by phi of x. And if we do that, when we do that, I mean, we're going to take this, we're going to take the inner product of this with phi of x. And when we do that, we're going to have this equation here. And again, you may recognize this as the kernel function. So we have the function, we have the model now written again in terms of kernel functions. And this is your kernel trick. You see, all you need, so you actually don't need this part here. You don't need the map onto that high-dimensional space. So the model is written in terms of these kernel functions directly. Okay.
Sorry, Roman, can we have a question?
Yeah.
Hi. Sorry, this is going to be a very, very basic question. Practical one. So given a complicated data set, is there like a systematic way to test if it's linearly separable or not? I mean, I realize that it's a very basic question.
Well, an easy way to test this is to perform classification with the linear kernel. So you just set this to be a linear function. And if the classification doesn't work, I mean, your data set is not going to be linearly separable, because that's one of the best.
There is no stronger mathematical sort of theorem, like rather than just like trying, and if it fails, then it's not linearly classifiable.
Yeah. So you could. Yeah, I don't know. I don't think so. I don't think, because in general, like you're thinking. So in general, actually, yeah, I don't think so. I'll think about it, but or do some googling. But I don't think you can a priori say like if you have a high-dimensional data set, I don't think you can a priori say. I guess perhaps PCA could help there, but yeah. Since I don't have a good answer to this, maybe we should just move on. I'm not aware of a good way of. So what I would do, I mean, if I had this question in practice, I would just do SVM with the linear kernel, and as we will see in a minute, I'm gonna do that for that data set to show that. And I always do that, and usually so because we're solving a convex problem. So it's very easy to train the SVM, and so if the data set is linearly separable, it's going to be very easy to classify it, and it's with the linear kernel also, and yeah, so it's going to be fairly straightforward. So that's what I would do if I had this question in practice. Whether there's a mathematically rigorous way to tell just by looking at, for example, the covariance matrix. Perhaps, but I don't know off the top of my head. Sorry. All right. So, okay, yeah. So basically, we've got all these equations. To find a beta naught, we can use one of those for any point for which alpha I is not equal to 0. But again, these are not important details. So what is important is that we see again that the solutions here are written in terms of kernel functions. Okay. And again, I guess one key difference between kernel ridge regression and Gaussian process regression and SVM is that in SVM, you're going to basically fix the kernel function. You're going to choose the kernel function, and you don't muck around with it. You know, you just fix it, and then you're finding, by fixing it, you're basically fixing the RKHS, and then you're finding this coefficients of I. With kernel ridge regression and Gaussian process regression, you have to really optimize the parameters of the kernel functions. And the way kernel ridge regression and the Gaussian process regression approach this is different. And that's going to be the main difference between the two approaches. Like I said, kernel ridge regression simply looks at the validation error and tries to minimize it, you know, by some sort of a grid search of the, you know, you vary the kernel parameters by grid search, and you can do that because there's not many of them. You know, those kernel functions are parameterized by a small number of functions, except that for some problems that they can be high dimensional, and then it's a problem. In the Gaussian process regression case, you maximize what we call a marginal likelihood, but we'll talk about that. Now, in the SVM case, you fix the kernel, and again, this is important. This is the reason why most of quantum machine learning work has so far been focusing on the quantum analog of the SVM, because as you will see later, evaluating those kernel functions on a quantum computer is actually very expensive. And you know, yeah, so you want to be able to do this only once, and then you know, perform classification, you know, or build an accurate model by finding those alpha coefficients. With kernel ridge regression and Gaussian process regression, you may have to evaluate those kernel functions many more times than in SVM. Okay, but that's a side remark. All right, so it may be useful to compare SVM and ridge regression since we're talking about this. So one way, so we started by saying that we need to minimize that, so which is equivalent to maximizing that margin, you know, the distance from the hyperplane, subject to this condition in kernel SVM. Okay. And so, but we could also just take this equation and write it like this, and then we could think of this problem as a problem, well, as a problem of minimizing this function. What this plus here just means that we're, you know, we're looking on the positive part of this function. Okay, so now this looks like a problem with this representing the cost function and this representing regularization. Okay, so basically the difference between, so this is what we call hinge laws. So you see the red part here is the same as the regularization term in ridge regression, and this part here is going to be different, and this is called hinge laws. So basically, if you want to compare them side by side, ridge regression is basically one where you have this term here with this sort of regularization, and SVM, the only difference is just this term here. But that's just something to note. Okay. So again, you know, some popular choices of kernels for kernel SVM. Yeah, so let's look at this example of two classes that I mentioned earlier. We can classify them, well, first with RBF kernel. The RBF kernel works for this perfectly. So if you want to, yeah, so if you go do the numerical analysis that I just outlined with the RBF kernel, you're going to produce this line. So this line here is going to be the separating hyperplane, and these two dashed circles, they're going to be represent the basically the edges of that slab. So basically they would correspond to these blue lines here. Okay, so you know, if you try to solve the same problem, oh, where is it? Oh, went all the way to the beginning. So if you try to solve the same problem with the linear kernel, and this is what I mentioned earlier, you won't get anything good, right? So this is what you would get. So this is what you would get with the linear kernel. And right, so you won't be able to classify the data. Okay. All right. So you could try other kinds of kernels, like the polynomial kernel, for example, is going to give you something like this, the polynomial kernel of degree 3, and the polynomial kernel of degree 6 is going to give you this. Okay. With 100, you get something like this, which I think is a result of overfitting. And you could do the same for something that looks more funky. And again, yeah, this is what you get with SVM. I'm going to move on, and so what time is it now? So yeah, we still have 20 minutes or so. I'm going to move on and discuss now Gaussian process regression.
Roman, we have a question here.
Yeah.
Yes, maybe before. Please, what?
Go ahead, please.
Okay. Before you move on, you said that the kernel ridge regression is different from, for example, a neural net, because in a neural net we explicitly try to fit that transform, and in a kernel ridge regression we choose that transform in a way. Could you whether do like a nested kernel ridge regression where the x and x dash of the kernel would be the outputs of a previous layer, or would that no longer, like, he gave all these conditions for what would be a proper space for?
No, yeah, that people do that. I mean, like maybe more in the context of Gaussian processes, where you can actually build what people call deep Gaussian processes, just like in like deep neural networks, right? Then analog of deep neural networks. So yeah, it's not. Well, it's actually what you're talking about is sort of analogous to the algorithm that I will present tomorrow. The algorithm. So our goal will be to build something like this, but models that can, for example, extrapolate beyond the range of data. Okay, and if you want to do that, you can't really do that with simple kernels like the ones I mentioned. And so you want to build more complex kernels, and you want to build them in a particular way. So you can't just build them arbitrarily. And so I'm going to present an algorithm that does that. And so that algorithm starts with simple kernels and then combines them into more complex kernels. And it probably will produce something like what you're thinking about. I guess that the final kernel that I would be getting out of this algorithm could be represented by some sort of a neural network diagram. Yeah, so maybe we can wait till tomorrow and discuss this again.
Okay.
But yeah, and think about it, and I guess if you have any ideas for how to build kernels, we should definitely discuss this. Yeah. Okay, so I'm going to move on to talk about Gaussian process regression, which is actually going to be the method that I will use for most of the applications that I will discuss tomorrow and the day after tomorrow. It's a regression problem that we're going to be talking about again. So what you want is to build a regression of this sort of data with noise. And we're going to see that if you build a model with zero noise variance, you're gonna have a model that overfits. With noise variance, you're going to have a model that's regularized. So basically, we'll see that including noise in Gaussian process regression is equivalent to regularization in kernel ridge regression. Okay, we're also going to see that you can what Gaussian process regression offers you is the Bayesian uncertainty of the model in addition to all the other features. So I've given Anna a sample code that basically builds Gaussian process regression of a function that like this with two different libraries, the scikit-learn and the TensorFlow. The approach is, I guess, quite different. And TensorFlow is more explicit in how everything is done. I mean, like the code I gave you based on the TensorFlow part is more explicit. So I suggested to take a look at it, and I guess you'll have time to play with it. And so if you have any questions, let me know. But you should have access to this file, I guess.
Yes, yes, we will work on it on Saturday.
Good, good. Yeah, it's good that it's not today, because I think we need to learn some more theory for that, for the exercises that I recommended you to do. Okay, so we've already learned a powerful and general regression tool, which is kernel ridge regression. Kernel ridge regression is a workhorse of many applications of machine learning. So why do we need another regression model? Now, Gaussian process regression does everything that KRR does, but also allows one to calculate, first of all, the Bayesian uncertainty of our predictions. And as we will see, this can be used at least for two powerful applications. One is Bayesian optimization that I will describe tomorrow. And we're going to be using Bayesian optimization, for example, for solving inverse quantum problems. And another powerful application of this is a way to build better kernels. Okay, again, we'll talk about that tomorrow. Okay, so what is a Gaussian process regression, or what is a Gaussian process, first of all? Yeah, consider the following regression function in an n-dimensional space. So you have a linear regression. So you have a linear regression in an n-dimensional space. You have n plus 1 of these coefficients beta here. Okay, and let's say each of one of these functions, phi sub I, is some nonlinear function of x. Okay, what I'm actually depicting here is a single layer neural network. Okay, and so these functions here could be like some sort of activation functions. Okay, and x is a p-dimensional input vector. So we're working with a p-dimensional input space here. So like I said, this equation here depicts this sort of a neural network here. It's easier to think about it in terms of a neural network diagram. Okay, so now if all of the parameters of the neural network are fixed, then of course the neural network is going to produce for each value of x, it's going to produce a single value equal to f of x. Okay, but what we're going to do now, we're going to replace each one of those coefficients. See, these coefficients beta are the inputs into the direction. No, not the inputs. The inputs into this output, into this output neuron. So they're basically the coefficients with which you combine that pre-multiply those the output of these neurons. So what we're going to do, we're going to replace each one of those beta coefficients with a random variable. We're going to promote each one of those coefficients to a random variable, and so each is going to be distributed according to some distribution. Okay. Now, since the variables are random, each time we draw a value for beta naught through beta n and evaluate the output of the neural network, it will produce a different and random result. So the output of the neural network for a fixed x is going to be a random variable, and the neural network will become a Bayesian neural network. Okay, so if we plot the output f of x of a Bayesian neural network as a function of x, so imagine this is x, and for any given value of x, we have a distribution of values, right, of output values. So if we plot the outputs as a function of x, it's going to be just a distribution of functions. Okay, and each one of those functions corresponds to a different combination of beta naught through beta n. Okay, so how do we use such a neural network to model data? Okay, so one way is there a question? No.
I don't.
So yeah, okay, good. So one way is to select only the functions that go through our data points. Like you said, these are our data points, the red dots, and so why don't we select only the functions that go through the data points and then discard all other functions? Okay. Now, in principle, this can be done, and people do that sometimes with Markov chain Monte Carlo, for example, approaches. But in practice, it's quite difficult because there's just too many functions to go through. Even with Monte Carlo, it's going to be very difficult to sample the functions and build those sort of distributions. simply because we're dealing with like the number of parameters in this neural network is very large. So perhaps the Bayes theorem can help us. So if we denote, let's first introduce some notation. So let's denote by theta collectively all of the parameters of the neural network, especially the parameters that we're going to treat as random variables. Okay. So the output of the neural network is a distribution of functions, which we're going to call P of theta. So our goal is to find the functions, we're going to call this functions theta, that give a good description of the data. Our data is going to be in the form of the matrix X, which specifies basically the positions of the inputs, and these are our observations, Y. So we're going to call P of theta X the unconditional distribution of the neural network outputs at the locations of the input space given by X. So if we look at where our training points are, the unconditional distribution of the neural network outputs is going to be this. So what we want actually is to condition this distribution by Y. So this is going to be the conditional distribution of the neural network outputs at the locations of the input space given by X, conditioned by the observations Y. Okay, so this is really what we want to obtain. So we want to condition our distribution by Y's. So the Bayes theorem gives us this conditional distribution, right? You know the Bayes theorem, right? So it allows us to write this in terms of this, and this quantity here is what we call the likelihood. Okay, and okay, so we can in principle calculate this. So this helps, but not much yet, because even if we could calculate this, how would we use it to make predictions? Okay, our ultimate goal is to make a prediction of some quantity Y, the observation Y at some arbitrary point X star, right? So we can write an equation. So if we have this, we could take this and we could multiply it by this, and we could integrate it over theta. Okay, and that will give us the probability of Y star, right? So within the Bayesian approach, the predictions are always probabilistic. so this will give us the probability, and then we could use the mean of that distribution as our prediction, for example. The trouble is, these integrals are extremely high dimensional. Okay, you see, if you look at theta here, remember theta denoted collectively the parameters of the neural network. So how many of them are there? So if we consider a modest neural network, like with something like 20 neurons, we have something like 61 parameters. So we have to do like 61 dimensional integrals in this equation. And that, of course, is a modest case. And, so basically this makes Bayesian machine learning very difficult. Well, it would have made it very difficult had it not been for Gaussian processes. So this is where Gaussian processes actually help. See, if you now take this neural network and increase the number of these neurons to infinity, see, what are we going to have? We're going to have basically, so each one of these connections here is going to be a random variable. And so this output here is going to be a sum of random variables, an infinite sum of random variables. Okay, so if you let n go to infinity. And the central limit theorem tells us that if you take a bunch of random variables, a lot of them, and you add them up, then the resulting distribution is going to be Gaussian under some subtle restrictions, but let's not worry about that. Okay, so basically what we get is that a Bayesian neural network becomes a Gaussian process if we make the number of neurons in this hidden layer large enough. Okay, this was actually a surprise to some people, back in the 90s when this was discovered, because so the person who I think discovered this was a person whose last name is Neil. He was a graduate student at the University of Toronto, and he was basically looking at the ability of Bayesian neural networks to make predictions, and he was looking at he was making these neural networks bigger and bigger, and of course, as you make neural networks bigger, you would think that they would overfit. Right, so as you make them bigger, there's more parameters. You would think that they would be more prone to overfitting, but what he discovered then is that if you make the number of these hidden neurons large enough, then you actually have a Gaussian process which is much less prone to overfitting than neural networks. And basically, what is a Gaussian process again? It's a distribution of random functions that is normal, right? So if you now take this distribution and cut it in the vertical direction, at any position of x, you're going to have a Gaussian distribution, and that's so f of x is a Gaussian process. Now, the fact that this becomes a Gaussian process helps a lot, because the integrals that I told you that kill this, that makes it extremely difficult. They, in the case of Gaussian processes, they can be dealt with analytically. Now, I have a lot of equations to show how this is done analytically, which I don't think, what's that?
Can I ask a question?
Yeah.
Can you go one slide back?
Mm-hmm.
Okay, so here, because this is pretty awesome. So with this n, we go to infinity, right?
Mm-hmm.
And instead of overfitting, which would be expected for regular neural networks, we have something which is even less prone to overfitting. But this is only like it's under the assumption that the weights are drawn from the distribution. There's this randomness, right? This is the crucial part.
Yes.
But are there some conditions on what the probability has to look like? Because I imagine when they are like kind of narrow distributions, then kind of we converge to regular neural network, right? So am I wrong? Like,
no, as long as they're random. So I mean, like it basically talking about the restrictions on the central limit theorem. So I mean, we have to talk maybe about that. So strictly speaking, the central limit theorem says that, I mean, I have to recall it now, but I think it says that the random variables that you sum over, they have to be identically distributed, but that can be relaxed. Yeah, but other than that, I don't think there's any restrictions on the distributions, for example, don't have to be Gaussian. They don't have to be like they can be uniform distributions or anything. And
I think the only restriction is that the first and second moment of the distribution must exist.
Yes.
If infinite, then you go to these lazy flights. And such.
That's right. Yeah, exactly. That's a good way to put it. Yeah. Yeah, I guess that's the answer to this question. And then, so because a lot of times people will think that in order for this to become a Gaussian process, the beta coefficients have to be normally distributed, but that's not the case, because this is really the beauty of the central limit theorem that makes this a Gaussian. And why is it less prone to overfitting than the neural network? Well, it's because the Gaussian process is actually entirely determined by the mean function, and the mean function, of course, is the one that connects the means of those Gaussians, and the covariance. Basically, if you take two Gaussians here at two different positions of your input space, they're going to have some covariance, and if you look at it as a function of x, then you're going to have a covariance function. So this distribution of functions is entirely determined by the mean function and the covariance function. There's a lot fewer degrees of freedom, and that's why you basically don't overfit as one would expect.
Yes, exactly. So I mean, but what I'm aiming at, so people are trying to, so there is this limit, right, with like regular classical neural networks, that when you have a large number of parameters, you go, oh, okay. However, maybe is it only for one hidden layer, or?
Oh, I don't think so. I think that will apply. Yeah, it doesn't matter really if it's
Okay,
one or
because yeah, what I'm aiming at, people are trying to like decide what's going on when you have many network parameters, and there is this regime that it is not overfitting, right? And people are trying to come up with the reasons why. And maybe I'm wrong, but I never heard about like proof going through this Gaussian process. But is it actually how you can use it, or
well,
yes, sorry, go ahead.
Yeah, it's I don't know actually, because we're now talking about a Bayesian neural network, and it's quite a bit different from the regular neural networks, right? So there's parameters that do have to be random variables, and much of this. I mean, like I have seen papers where people make those connections, but much of this, I mean, most of this cannot be actually used to inform what happens in deterministic with deterministic neural networks, to the best of my knowledge.
Okay. Okay. Thanks.
Yeah. Okay. So I guess. Yeah, I'm gonna have to skip all that math. We have like 5 minutes left, but again, this is what a Gaussian process is, and the beauty of it is that because now we have those Gaussian distributions, the integrals that we mentioned earlier, they can be dealt with analytically, and those the predictive distribution. So basically, yeah, this is a bunch of math that I was going to go through that we're going to skip. So, but yeah, so basically what you arrive at these equations here. Actually, even, sorry, there's too many equations. Yeah, you arrive at those equations here. And what those equations are, they're actually the conditional mean and the conditional variance of the Gaussian process. Because again, the ultimate goal of building a model of the data is to go from something like in the top graph here to something like in the bottom graph here. Now, I started off by saying that these are Bayesian neural networks, but in the case of Gaussian processes, this distribution here is going to be a normal distribution of functions, and this distribution here is going to be a normal distribution of functions. So you're going to go from a normal distribution of functions in the top graph to the normal distribution of functions in the bottom graph. Now, and because everything is Gaussian, you have analytical equations for the mean of this distribution, this green curve here, and the variance of this distribution, the conditional distribution. So the bottom panel here displays the conditional distribution, and the equations for those are this. So this is what they are. And you can see that they are, again, can be written in terms of the same kernel metrics that we saw before. So this is your observations, and so basically, so this is very similar to what we saw in the case of kernel ridge regression. Now, this is an additional benefit of Gaussian process regression, because again, this is what we don't have in kernel ridge regression. So this is the Bayesian uncertainty of the model. It's a function of x star, and this is also a function of x star here. But again, what we see is that everything is determined by the kernel functions, and so the choice of kernel functions is going to be very important. So this we have to skip because we didn't talk about those covariance matrices. Maybe I'm going to conclude by yeah. So again, by showing this formula, right? So this is again the model, which looks identical actually to the one in kernel ridge regression. Well, this is actually the kernel ridge regression. So this is the one from Gaussian process regression. And what this here is actually the variance of the noise. So you can see that this formula is identical to what you have in kernel ridge regression, except that this regularization parameter is the variance of the noise. And if you go when you go through the exercises that I ask you to do with that in that notebook, the Jupyter notebook, there's a so I suggest that you first build the regression, Gaussian process regression of the data without the noise, basically assuming sigma squared here equal to 0, and you'll see how that will lead to overfitting. And then you include the what we call white kernel, and which basically represents this noise, and that will fix that problem. So I think I've designed that Jupyter notebook for you to do that. Okay. So there's one more thing that I wanted to say before we end today, and that is again the question of how the Gaussian processes are trained. Again, as before, one starts by choosing this kernel function. And then the parameters of this function are varied to basically maximum. So unlike in the current Ridge regression, you actually don't deal with the validation error here, but you're maximizing basically this probability here, or you're maximizing the likelihood. Well, actually, this is marginal likelihood. What this is actually the term in the denominator of the Bayes theorem, which is this quantity here, and basically, yeah, it's integrated over those parameters, and that's why we call it marginal likelihood. But the beauty of this is that because this is Gaussian, you know, if we're assuming Gaussian likelihood, and for the priors, we can also, I think, deal with, you know, assume them to be Gaussian. So everything is normal. So these integrals can also be done analytically, and this quantity can be written in terms of the, I think I have it right here. Yeah, it can be written in terms of the logarithm of it can be written in terms of the kernel metrics. So basically, have a closed form equation for the logarithm of the marginal likelihood, and this is what we usually maximize by varying the parameters of the kernels in order to train Gaussian process models. Okay, so I'm gonna send you this slide so you can go through the equations if you want and send me your questions. But I think I've made all of the points I wanted to make today. We have enough to work with tomorrow. So I'm going to end here. And like I said, you know, submit questions, I mean, either through Discord or through, well, by email, and I'll try to address them by tomorrow. So this is, yeah, all I have for today, and we're right on time. So what do we do now?
Thank you very much, Roman. I
We
don't know
clap.
if we have more questions, we can.
Yeah, we can chat. I mean, like, you know, it's only 2 a.m. For me, so I mean,
Oh my God.
it's very early in the day.
Maybe
Maybe
let's
let
make it
him
really
sleep.
Yeah. Okay.
Yes.
Then.
So if you have questions from
exactly.
today, please send to him either by email or by Discord.
Yes.
Okay.
So have a good sleep.
Thank
Thanks
you
a
very
lot.
much, Roman, and go to bed.
No problem. Yeah. You have a great day.
Thanks.
Thank you.
Bye now.
Bye-bye.